All right, we're going to continue now with regression. Remember that thing we were doing before exam 1. And last we left off was we talked at the coefficient of determination. So we worked through 3 things to measure how well a regression does its job. Okay, and the first one was saying if you have data and in the absence of any other knowledge than the data itself, the simplest statistic you can give is the mean, is the average value. You can give the median, but the mean is most likely the most descriptive statistic you can give. And then we measured the spread of the data around the mean, and we called that an error, but it was the standard deviation, but part of it is also an error, making the mean accountable to be the truth, essentially, and how much is the data spread around that mean. And part of that standard deviation, we defined this term ST, just call it ST. It essentially measures the spread of the data around the mean value y bar. So that's magnitude of error prior to regression with respect to the mean. And then we said, okay, let's do a regression now. Remember the height versus femur example, and the data was lined up almost along a straight line. And then we put a straight line there, and we asked the question, okay, that straight line is going to split the data also above it and below it. Let's measure that spread, and we call that the standard error. So that's equivalent to the standard deviation around the regression line. So for the standard deviation, it's the deviation of the data around the mean. The standard error is the deviation of the data around the regression line. Now, we also defined SR, which is a similar measure to ST, and that was the error, the spread of the data around FI, which was the line. And remember, the mean value is just one value. That's why you see Y bar up there. But the regression line has a different value for every data point, and that's why you see Fi. So for every point Xi, you're going to have Yi and Fi, and that difference squared, you add them up, gives you a measure of the magnitude around the regression line. So that's standard error. If the data in general is normally distributed, don't worry about that now, but in general, 68% of the data will fall within plus or minus standard error, just like the case with a standard deviation, plus or minus 1 standard deviation. And then we said, okay, now ST and SR are related somehow, and we said that SR measures the improvement doing regression versus just using the mean to describe the data. So if we use the mean to describe the data, we're going to have standard deviation and ST. Then we do regression thinking that it's going to do a better job to describe the data. So that's going to give us SR. And then we said, okay, if SR is smaller than ST, then we did a better job. But in the worst case, SR will be equal to ST. It means regression didn't do anything, didn't improve on the data. Okay? And using that concept, we defined the coefficient of determination, which took the difference between the error prior to regression and the error after regression. So that gives us the improvement that the regression has made. And we normalized that simply by the data on the mean. And that gave us the coefficient of determination. And again, if SR is much smaller than ST, it means we reduced the spread of the data by doing regression. Then R squared is going to be close to 1. So that's a perfect fit, significant improvement over just using the mean value. And if SR is almost the same as ST, so we didn't make any improvement by using regression, then our R squared value is going to be 0. It's a bad fit, right? So if SR is almost ST, it becomes 1 minus 1, and you'll get 0, okay? All right, now we're going to have a lot of activities back to back right now. And I'm going to wait for Mokbel to get the phone. Okay, so I'm going to show you some data next. Okay, these are data points, X and Y data. Don't worry about what they mean or the units. Just look at how the data is distributed. Okay, and this next activity is going to be a group activity. No calculations involved. Okay, no calculations involved. But I want you, just based on what we just discussed, SR and ST based on the mean and on the regression line, I'd like you to do the following. Take these data and draw a regression line. Compare conceptually what ST and SR are going to be. Is SR going to be smaller than ST, or is it going to be the same? Remember, ST is the measure of the error around the mean. SR is the measure of the error around the regression line. And then estimate the R squared value. You got 2 minutes. I want to hear some buzzing. Go. Yeah, so draw the mean, and draw the mean, draw the regression line. Yeah, draw the mean, draw the regression line. Think about it. Did we improve in the spread or not? You like what?
I like it. It makes you really think about it from an intuitive standpoint.
Exactly. Exactly.
So.
It looks like you have the answer.
Yeah.
What are your name tags? What's your team name? I don't remember your team. I know your name, Seipo. But come up with a team name. What is that? Struggle train. All right, time. Okay. All right, let's start with the bug zappers. Bug zappers, yeah? Let's start with the first question. Yeah, just through the middle, right? Yeah. So does anyone disagree with that? Yeah, so the regression line is probably just going to be following the trend, right? It's going to be along the middle. Okay, so question 2, comparing ST and SR. We got, let's see, the Professor Sad group.
I'm working on the new side. So decided that the mean would probably be right around 0, which is where our regression line fell. So the ST and SR are going to be identical.
Fantastic. Okay, did everyone hear what Conrad said? So he said that because the regression line falls pretty much on top of the mean, then our spread of data around the mean is going to be equivalent to the spread of data around the regression line. And therefore, we expect SR and ST to be the same. So who wants to take the last question? Team Dumpai?
We were thinking maybe
It's going to be 0. It's going to be pretty much 0. Yeah. Does anyone disagree with that? Because SR and ST are the same, we didn't make any improvement on the data, on using the mean. So regression didn't give us any improvement, right? So we expect our R squared value to be a very bad fit and to give us 0. So let's see things in number. All right, so if you draw the mean, that's the mean. It's about 0, almost 0. And then you draw the regression line. The equation for the regression line is the slope is almost 0, right? It's just almost 0. And the intercept is 0.0058, and the R squared value is again almost 0, as we expect, okay? All right, let's see another set of data. This time, you got 1 minute, because now you have experience how to process this. What about this data set? Okay, go. You got 1 minute. A temporary team name? I'm not sure I want to go on record with your team name. It's okay, you can change. Academic masochism. All right, time. Okay, I'm going to ask for volunteers now because you all know the answer. Do I have any volunteers? Okay, then, all right. Yeah.
The line is just, it's a linear line.
Yep, it's all along the data. And then what do you expect for?
We expect that our ST value would be like right around 7. We assume just an average of points.
Okay, so that would be the mean value. Yep.
And then our SR would be like really close to 0.
Yeah, because our regression. Yeah, so what she's saying is that the regression line, compared to the mean value is going to be around 7, right? But then the regression line is going to follow the data very closely. And the spread of the data around that regression line is going to be so small, it's almost 0, definitely much smaller than ST. So that would give us an R-squared value right around 1, which would probably mean this data is doctored, which it is. Okay, so I happen to doctor it, and that's the R-squared value. Okay, so when you see data, think about it intuitively, what these mean. Standard deviation, standard error, R-squared value, they're just numbers to help you process these data, but think about what they mean before you rush in and do calculations. And run the calculation, you may see a number that doesn't make sense. Then interpret that number in light of what the data looks like. And always plot your data, always plot, get familiar with it. Okay? All right, so now we're done with assessing the goodness of a fit. Thank you, Mokbel. You can give me my phone back, please. Thank you very much. All right. Thank you, Mokbel. Okay. Yeah, he can take good videos, so he. All right, so far we've done a regression curve. Let me make sure I still have battery here. Okay, so on a straight line, that was our model. You can think of it as you're modeling a set of data, okay? And our curve, our model was a straight line. What if we wanted to use a quadratic? Something like this, okay? A2x squared plus a1x plus a naught. So again, this is not interpolation. With interpolation, we would need at least and at most 3 points exactly to get these coefficients, a2, a1, and a0. But with regression, you're trying to fit these 3 data points into thousands of data points. So that's how we introduced the minimization of the error. Okay, so now my question to you is, if we were to do a regression on this one, recall the regression derivation, do you think, and I want you to individually think about this, and think quietly, so no buzzing, okay? Do you think we will get a system of equations, and why or why not? A linear system of equations. So if we were to do a regression on this formula, okay, you may pull up your slides on linear regression where we defined the error and then we defined the minimum. We looked for the minimum of the error and that resulted in equations with two unknowns. Do you think here we will get a linear system of equations? You got 1 minute. Go. Individually, please. Try to do it individually. Okay? And then you can talk to each other once you have an answer. The answer is in the slides, but I recommend that you don't see that because you're going to have to back up your answer. Okay? Okay, time? All right. Let's see. Maddie, do you have an idea? Yes or no? Okay. That's the correct answer. Yes, we will get a system of linear equations. But why?
This is like going back to what we did previously and like trying to just get a curve to it. Like we did get like individual lines.
Yeah, but why do you think once we do the we're going to show that we'll get linear equations for A2, A1. But just looking at this equation, how do A2, A1, and A0 show up in the equation? They show up linearly. They're not under logs or complex, multiplied with each other. They just show up linearly. So don't think about the x squared and x because those are given data to you, right? We're going to pass these points through all the given points. So x squared is just going to be a number. Okay, so forget about that. That's why I put things in red. These are the unknowns. So our unknowns, they show up in this model as just a linear combination. Okay, so we're going to derive this and show you that actually, yes, you will get a system of linear equations. That's why it's called linear regression. Although we're fitting a quadratic, okay, and we're going to fit an nth order polynomial later on, we are still going to get a linear system of equations. So that's why it's called linear regression. Okay, not because we're fitting a straight line. Okay, be careful. All right. So again, we do the same process. We define an error. That's really SR. That measures the spread of the data around our model curve S. So that measures how far yi is away from fi, which is the value that's going to be predicted by the curve. Okay? So we're going to minimize this. We're going to minimize this. That's what we did. So if you plug in the formula for fi, so that's f of x, a2, x squared, etc., and you plug it in, that summation is over all the points, all the input points, going from 1 to n, if you have n points, okay? However many points you have. So that's just going to give you that entire summation. Now, we want to minimize this. And in this case, we want to minimize s over its three unknowns. Those three unknowns are a0, a1, and a2. So the same way we did with the straight line fit, we make the derivative equal to 0 at the derivative with respect to a0, derivative with respect to a1, and derivative with respect to a2. Now you have 2 minutes to actually calculate this and group activity. So pull up your papers, and I want you to find the expressions for this one. Please do it by hand. You can look at the slides. It's not going to help you because exam 2 is going to require you to do this by hand. Okay? It's going to require you to do this by hand. Go. If you can't do all of them, at least do one of them. Okay? At least pick one and do the derivative with respect to either one of those. Divide and conquer.
Okay, I'll take 8.
And remember the derivative of u to the power n. simple. With respect to a naught, you fix everything else is constant. It's 2 derivative with respect to a naught times the thing to the power n minus 1. Okay? Sounds like an exam. Well, I put the formula there. The derivative of u squared un to the prime is n u prime un minus 1. Okay?
You go to Wolfram Alpha.
Sure, you can do that. Thanks, Jeff. All right, time. I'm going to show you the answer. We did this last time, but I'll show you the answer, and you can try to verify it at home. Come and ask me if you're struggling with it, but if you got something along those lines, you are correct. Now, again, when you look at A0, A1, and A2, they show up linearly in these equations, okay? And it's these equations that we are going to solve to find A0, A1, and A2. So we have 3 equations, 3 unknowns. That's the beauty of minimizing the error, is that the minimization gives you enough equations for your unknowns, and you're done. You don't have to worry about how many data points you have anymore, okay? And then we'll reorganize things a little bit like we did last time. And notice that I dropped the minus 2, and then the summation of A0 in the first equation gives you n, which is the number of data points that you have. And then you consolidate all terms and make them, multiply them with the unknown. So you see red is unknown, and all the other numbers, they're known. Okay, so whenever you see these xi's, they're known data. These are the data that are given to you again. Okay, then you write this in matrix form, and indeed you get a system of linear equations. Okay, and you could have predicted that by looking at the formula for SR, or that summation, the spread of the data around Fi. The unknowns show up linearly over there. That's what would have told me that this is going to result in a system of linear equations. Okay, so just like we did with regression for a straight line, we do the same for a quadratic. Okay, so now the question is, can we generalize this to an arbitrary polynomial of order m? Okay, so now we're going to get confused between n and m. So we're going to use n for the input data points and m for the polynomial order, okay? And I will try not to mess with you on the exam and switch the nomenclature, but we're going to stick with m for the polynomial and n for the data. Okay, now if n is equal to m, you are going to get an interpolation. You do an interpolation, okay? But if n data points, you have more data points than polynomial order, then you got regression, okay? Then you have regression. Now in this case, yes, we will get a system of linear equations. And I'm going to ask you the following. For a straight line, this is the matrix structure for the system of equations. For a quadratic, this is the structure of the equations, okay? Now, I'm going to ask you to infer the structure for an mth order polynomial, okay? You got 1 minute, work in groups, look at patterns, look at go row-wise or column-wise, okay? Every time we added a degree, we added a summation, okay? And then we increased the order. So we had n, some xi squared was going to come in after that. Some xi cubed, some, Do it for an mth order polynomial. Try to write it down. Pardon me?
Oh, I'm just.
Oh. So Just continue the matrix. Just follow through with the matrix. So, go from a quadratic to a cubic, and then from a cubic, to a fourth order polynomial, and then a quintic, and then it will just generalize naturally, okay? Just write the equation. Put 3 dots, and then write the last element. What's important is to recognize the size of the matrix, okay? First order is 2 by 2. Second order is 3 by 3. Mth order.
Sorry, just looking at the Excel.
I'll give you 1 more minute. Do it either row-wise or column-wise, and then just fill in the gaps. Do 1, 2, 3 terms, and then dot, 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 and then the last term. Okay? You guys are working together. I guess you have it figured out. You got it all figured out. Okay.
I think.
Yeah, but you have to write it in matrix form. Yeah, so I want you to write the matrix form that looks like this. Exactly like this. So write the system of equations that you solve to find am minus 1 all the way to a naught. Okay, that's so write it in matrix form. Yeah, I think you got it. Okay, okay. Team Bug Zappers is always on top. Good stuff. All right, you stand by your answer.
Stand by it.
Okay. Okay, good. Right. I don't care. I don't care. I don't care. do whatever you have to do. Okay. Okay, time. All right. So I'm gonna volunteer individual columns. I'm gonna select answers for individual columns. I've seen most of you have figured it out, so maybe we'll start with the Team Chocolate Bin. That's a funny name. Ryan, do you have an answer for at least the first column?
Yeah, so the first column starts at n,
Mm-hmm.
and it goes increasing down by summation x with summation x2, and then it goes all the way to summation x to the n.
Correct. Yes. So just following the pattern over here, n, some xi squared, some xi cubed, dot, 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 all the way, some xi to the power m. Okay? And then this column over here will contain a naught, a1, a2, a3, all the way to am. Okay? So what's the second column? Ember, you got an answer? The second column, yeah.
So the summation of xi,
Uh-huh.
summation of xi squared,
Uh-huh.
to the summation of xi to the n plus 1.
M plus 1, right? So you see the pattern. Every column we move towards, we increment the power of xi by 1, okay? So what about the third column? Let's see, guys, back. What's your team name? You don't have a team name yet. All right, yeah.
So it's similar pattern.
Uh-huh.
Third column, so
Yeah,
we're
yeah.
gonna go until
So it starts at xi squared, and then
It goes all the way down to
m plus 2. Yes, correct. And so on and so forth, right? And the right-hand side, same thing. Some xi yi, xi squared yi, xi cubed yi, all the way to what? M plus 1, okay? And so all the way to m, actually. So I'll show you the answer. This is the matrix, okay? The size of the matrix is m plus 1 by m plus 1. Why? Because just think about it. Before thinking of the size of the matrix, think about the solution vector. What is the size of the solution vector? A naught, A1, A2, A3, all the way to m. That's m plus 1 entries. And for the system to be invertible, to be solvable, our matrix better be m plus 1 by m plus 1. Otherwise, we won't be able, we would have either less equations or more equations than there are unknowns. Okay, so that's one way to double check your thoughts, okay? Now, we'll probably address this later, but don't blindly apply this formula to a system, to a polynomial I give you, because all I have to do is knock out A1 over there, and it will change the structure of the matrix. Okay? So I've seen people in the past put 0 instead of A1. That doesn't make sense. What you have to do, you have to remove the entire row and the corresponding first column to make that work. But instead of doing so, just go back and try to derive the equations, okay? And very likely, I'll give you like a second order polynomial, for example, and knock out A0, right? Or a cubic and knock out A2 and A1, right? So you'll end up with 2 by 2, right? So always go back to what you're solving. How many unknowns do you have, okay? Do you have 2 unknowns? Then your system of equations needs to be 2 by 2, okay? 2 equations and 2 unknowns, all right? Okay, so now let's go and look at, so the beauty of this formulation, though, is that we can implement this manually for an arbitrarily shaped polynomial the way we like it. We can implement these matrices the way we like and invert them and get a solution. If you want to use a package like Python or MATLAB, you are bound to a full polynomial. So you cannot say, I'm going to make a polynomial ax cubed plus b. You cannot do that in Python, not that I know of, at least. So it would have to have all coefficients in there. So the power of doing this yourself is that you can manipulate your model the way you like, and then you build the matrix and you solve it. But if you're doing just a standard regression, and most likely it's going to be straight line regression. So all of these are linear regressions. Be careful. So although this is a polynomial, and polynomials are nonlinear per se, it's still linear regression. Okay, because this, yes, Eric.
So I just have a kind of general question. So instead of doing a regression to a polynomial like a line, could you do a regression like to an exponential?
Absolutely, we're gonna get there. Yep, you can do to whatever you like as long as, so we will also discuss what's called nonlinear regression, and we'll learn how to solve that later. But if your model results in a linear system of equations, you can do whatever model you want, okay? So the general guideline, we'll discuss this a little bit later. The general guideline would be the way your coefficients for the fit show up. So if you had an exponential ax, that's not going to be, you're not going to be able to get a linear system of equations. Whereas if you had a e to the x, then a shows up linearly. Does that make sense? So we'll see, we'll touch on that a little bit later. But right now, let's see how we can do least squares in Python. We're gonna use, there are numerous ways, and you can pick whichever way you like. You know, I don't care if you want to validate your data, as long as you know how to use the function that you like to use, that you're using. I like to use polyfit because it can give me either an interpolant or a regression in one shot just by changing the degree of the polynomial. Okay. Remember polyfit, we used it to do interpolation, and we said if the degree of the polynomial was equal to the number of points provided, that results, pardon me, that results in an interpolation. However, if you remember when I said if you give a degree of the polynomial that is less than the number of points, then that is going to result in regression. I said that about 3 weeks ago. This is it. We're gonna do it today. So we use polyfit. We're familiar with it. You give it input data xi, yi, and you give it a degree for the polynomial. For linear regression, for straight line regression, n is 1. For a quadratic regression, n is 2. For a cubic regression, n is 3. As long as the size of xi and yi is more than n, okay? You will always get regression. The problem you were shown in your exam, that was a regression to a quadratic for the data set of the temperature versus time of day, which had about, I don't know, 24 points in it, okay? So let's, I have 2 slides here for some reason. Okay, so now I want you to pull up the height and femur data that we worked on last time, the notebook. If you don't have that notebook, I uploaded it to Canvas. So if you go on Canvas under Files, you will see Regression Activity Part 1, or actually get Part 2. Download Part 2 and put it in your, or if you have the regression notebook that we worked on last time, that same data, you should still have it in your Jupyter. Just open that, and I want you to use polyfit to regress that data using polyfit, okay? Last time we did it manually. We built the matrix, and we solved the system of equations using Lin algebra solve, inverse, whatever. Okay, now we're going to use polyfit. Okay, you got a few minutes. Let's see, we have the, I think it was called, yeah, I don't know, it probably doesn't show up here. So go to Canvas. If you can't find it, go to Canvas under Files and get the Part 2 regression notebook. Yeah, okay. Anyone having issues, let me know. I'll come and help you make sense of the notebook. You got it, Maddie? Yeah. Perfect. Yeah. Yeah.
It looks like what you have in here is like to do our own regression instead of using the polyfit.
Yeah. So that was the one we did last time?
Yeah,
or did you just download that?
This is the one I have last time, I think.
Okay, yeah. So all you need is the xi and yi, okay?
Okay.
Yeah, so all you need is the first 2 cells, okay, to do the polyfit. You want to do Part 2. If you're downloading from Canvas, download the Part 2. Or Part 1 if you want, but you only need to use xi and yi. I think, yeah, you should try to kind of do it at home. I'm going to try to post these recordings, but there's been some issues with the recording stuff, and posting the lecture with the group activity kind of tends to be distracting as you're watching it again. But try to follow at least with us now, and I'm going to upload this. So we're recording the screen. We'll upload it and then follow through with it. Yeah. Yeah, yeah. So there are some gaps in that notebook. Don't worry about those. Just all you need is xi and yi. For polyfit, all you need is xi, yi. So let me show you. Whichever part you end up downloading, okay, all you need is this guy and this guy, these 2 cells, right? You need xi and yi. What you're seeing is probably some question marks over here. Don't worry about that. All you need is xi, the fit using NumPy, okay? All right, so I'm going to start counting from now. 3 minutes, go. You can do it as group. You can do it individually. Working with groups sometimes helps when you're doing paired programming. One person reads or tells the other person and the other person types? So Jordan and Maddie, you're in the same group, right? Okay. Yeah, I want you to kind of just collaborate and nail this. I want you guys to come up with a name for the group. All right? And I guess you don't have a laptop. Do you want to follow? Yeah? You want to follow with him? Yeah? Yeah, so I'll show you the polyfit. And we used polyfit in the past. So you just use it the same way. Okay? Remember polyfit. You give it xi, yi, and n. It's going to return a set of coefficients. And then you evaluate the coefficients with polyval. And I'll show you another trick. If you need help, I'm here. Okay, even to remember how to use polyfit, how to use polyval. Remember polyfit? Yeah.
Why is mine getting messed up? Did I go wrong?
Okay, so what did you do here? Okay, so you got xi and yi.
Yeah.
Okay, and then what?
I just chose a number less than
Okay, so now this tree has returned the coefficients,
all right.
right? And then you're plotting, and you're plotting polyval. You're evaluating at where?
At yi, right?
Why?
Oh, would it be x?
What do you think?
It should be x.
Yes. See, you know the answer. There you go. All right, got an answer over here. Yes, Katrina. Why you don't have an answer yet? No. Okay, yeah, that's good. But don't plot the original data. Put them as points. Yeah, Jeff. You can look at the coefficients, but we want to plot the line. So use polyval to plot the line. Apply polyval on the input data. Right? That's how you plot it. Okay?
Figuring out what xe is in this case because we don't have a specific value.
No, so you can apply polyval on either one value or an array. Right? Yeah, so in this case, you want to apply it on what array? So to test your data, you're going to apply it to the input array, right? To the xi. So all you have to do is call polyval on xi.
So I just do it like that.
Yeah, so, but not polyval equal. Polyval applied at, right?
Oh,
Yeah,
nice.
yeah. But I want you to plot this. So I want you to plot, try to plot, yeah, polyval versus xi, right? So,
Okay.
so that shows you the line. Because polyval now is going to apply the polynomial or the line, okay, with these coefficients on these data xi, okay?
I get what you're saying. Okay.
Okay?
Thank you.
You got it, Natalie?
Would it be like
No, just plot it at. So no, xi would be your x values and polyval would be your y values, right? Because polyval is the straight line, okay? Let's see, Jeff.
I'm trying to remember how to do any plots. Like you.
plt.plot. Plot and then x comma y.
Yeah,
So x values comma y values, yeah.
X values are going to be
Yeah.
polyval.
No, the polyval are going to be the y values, right?
Oh yeah, yeah.
Right? Yeah. Yeah.
We are supposed to find. So it says we do need to use the both, like one is n equal to length xi minus 1 and one is n less than n.
So no, so over here, what I'm saying in this slide is that if n is equal to the number of points minus 1, that gives you a interpolation. We don't want interpolation. Right now we want regression. But what I'm asking is now to do a straight line regression. So n is equal to 1, yes. Okay, so once you do that regression, then polyfit is going to give you coefficients of the linear equation, A0 and A1, right? It's going to give you A0 and A1. And then with polyval, you apply A0, it automatically applies A0x plus A1x plus A0 at this point. Okay? Now you don't want it necessarily want it at 45, you want it at all the input points. Okay? Is this clear? Yes. Hold on, get it. Yes. No. Let's see. Show me what you got. No, why is order, what did you do here? When you say order is len x minus 1.
You're supposed to fit the...
That's a regression. We're not doing an interpolation, we're doing a regression. So your regression needs to be to a straight line, okay? We're not doing a polynomial fit, we're not doing an interpolation, we're not doing a polynomial fit, we're doing a straight line fit. Although a straight line is a polynomial, but we're doing a straight line fit. So your order, your degree of the polynomial needs to be what? 1. Okay? Okay? All right. Plot your original data as a scatter. Don't connect it with lines, so make them dots. Okay? Come on. Let's see what you got. Oh, beautiful.
So originally I did it using n. Sorry, I put all my stuff down there. So
Unacceptable.
polynomial, we would say n is the number of points minus 1.
That's interpolation.
Yeah. Oh,
Yeah.
Okay.
Right? Because if you have data points, you can fit a polynomial of, you can interpolate to a polynomial of n minus 1. So when you put n minus 1 over here as the order, it's going to do an interpolant.
Okay.
We don't want an interpolant. Yep.
Jagged,
Yep.
funky.
Okay. Okay. All right. Let me show you how I would do it. I saw some beautiful answers. Okay. Let's see. Okay. So this is the data. These are the data. And if you remember, we had looked at the data last time and we plotted it. And then we built our own regression by hand, right? And then essentially we got these numbers for the solution, okay, A0 and A1. Okay, so these are the A0 and the A1 for the regressed line, okay? And now we're going to do this with polyfit. So all we have to do, all we need is these data points, xi and yi. And what I'm going to do, I'm going to get the coefficients, coefs equal np dot polyfit, and you all nailed this. Polyfit, what does polyfit need? Xi, yi, and a degree for the polynomial. In this case, if you put the number of the input data minus 1, that gives you an interpolation. We don't want that. We want a number less than that, and specifically we want 1. We want the number 1 to do a straight line, okay? So we put 1 over here. And if we print the coefs, it's not going to give us anything. Because I had a typo. Okay, so notice what it did, but it inverted the order. This is A1 and this is A0. If you remember our coefficients that we obtained when we did this regression manually, this is what we got. That's really good because now we have a way to verify our implementation. So if you're in doubt, you're doing some work or homework, use some other capability to validate what you're doing, okay? And verify that you're doing things correctly, okay? And then, okay, so now we have the coefficients. You can go ahead and construct manually a function that does A0 plus A1x, or you can just call polyval on a set of data. Okay? So what I'm going to do, I'm going to apply polyval directly on the input data. And then I'm going to say plt.plot. I'm going to plot the original data, xi, yi, and I'm going to make them into little disks. And then I'm going to plot xi, and then np.polyval of coefs. So you give it the coefficients. Applied also at xi, I'm going to make this a line. Okay? What? Coef. Oh, coefs. Oh. But it was previously defined as coffs, so that's why it let it through. And this is exactly what we got last time. I hope I still have the plot down here somewhere. It's not here. Okay, so let me run this again. Okay, that was the plot we got last time. Okay, so they're the same thing. Okay, now the annoying thing about polyfit is it doesn't return to you things that are interesting like standard error, standard deviation, and r squared. It probably returns r squared, but you have to kind of pass some options. I usually just like to compute those myself manually. There are some more advanced statistics packages in Python that will return all these numbers for you. And you're free to explore those. Just simple Google least squares in Python. You'll see a ton of options. There's options with NumPy. There's options with SciPy. There's options with some statistics package. So, you're not limited to polyfit. Polyfit is just one option that we cover here in class. I like it because it's simple. 2 lines, you're done. Okay. Now, if you continue through this notebook, okay, what you're going to see is 3 gaps over here. Okay, 3 gaps, and one of them is for defining the SY, or actually the standard deviation, right? That's the standard deviation that had the ST in it, and then the standard error, and then the r squared value. Those are, we covered how we do this in class in one of the slides last time. So you should know how to implement those. Okay, just know that you should know how to implement those. Okay. Okay. Now I want to be done with linear regression today, or at least for linear models. Okay, I'm going to be done with that today. So we're now going to switch gears to another way of formulating the linear regression problems. That's called the normal equations approach. Okay, and I'm going to posit the problem that we looked at right now earlier, and trying to fit an mth order polynomial into n data points. Okay, actually you need a break. I think you need a break. Don't you need a break? All right, sorry about that. I need a break. So let's take a break, 3 minutes. Okay, come back at 3:05 and 6 seconds. Okay, 6 seconds. Taking forever to process, but so what we're going to talk about now is a simpler way of defining systems for linear regression. Okay, and it's just a different method. You don't have to use it, but it makes the implementation in Python way much easier. Okay, but it's only useful for very high order polynomials. If you're doing, first or second order regression, you don't have to worry about this. But we have to cover it for completion purposes. Okay. So if you think about the system of equations for general polynomial regression, this is what we had. Now imagine trying to implement this Python manually, trying to do this matrix. It's going to be really annoying. You're going to have to do some crazy loop and then add terms. It's really prone to errors and very annoying to implement. Okay, it's really very annoying to implement. But there's another way called the normal equations. Now the normal equations are derived from some higher statistics, analysis, but they just apply here by using just a simple observation of the system of equations. So I'm going to start by a simple example, as has been the case in everything I like to do. So we're going to take 3 data points: x1, y1, x2, y2, x3, y3. These are given to you, and we're going to go back to our original model for the straight line, a1x plus a0. Okay. Now, rather than going the least squares, defining the square of the error and differentiating it, what we're going to attempt to do is pass this equation through these 3 data points. So you pass point x1, y1, x2, y2, x3, y3. So you essentially evaluate that function at x1 is going to give you y1, at x2 is going to give you y2, at x3 is going to give you y3. Now, obviously, there's a problem with this system of equations because you have 3 equations and 2 unknowns. Okay, so it's an overdetermined system. You have more equations than unknowns. Okay, so we can't solve it. Okay, we know it's 3 equations, 2 unknowns, we cannot solve. And if you write this in matrix form, this is what you get. And the fact that this is not a square matrix, remember early on when we talked about linear systems, the matrix needs to be square for it to be invertible. Okay, this is a non-invertible matrix. It's 3 by 2. Okay, and we have 2 unknowns, so there are more equations than unknowns. We know this and we agree with this. However, if we make the following observation, while A equal B, or I should have called it phi for the coefficients, but the lowercase a contains the unknowns in the straight line regression. While this is not solvable, the following system is solvable. If you take A, transpose it, so rows become columns, first row becomes first column, second row becomes second column. You invert it and you multiply it by the entire system, this is actually invertible. So think about it. In this case, this was 3 by 2, and this will be 2 by 3. So 2 by 3 times 3 by 2 gives you a 2 by 2 matrix. Okay. Now we also claim, I'm going to claim that this operation actually results in the system of equations that we obtained earlier when we derived the minimum conditions for the ST, for the SR, sorry. So for our example of 3 data points, if this is A, 1, 1, 1, x1, x2, x3, just like we showed, then A transpose, you flip it, you flip the first column, becomes the first row, second column becomes the second row, and then ATA gives you a 2 by 2 matrix. Now if you remember, in our matrix for regression, we had n over here, which is 3, and we had some xi over here, and we had some xi over here, and some xi squared over here. So lo and behold, this operation resulted in the same system of equations that we obtained before. Okay? Now, interestingly, my claim is that not only is this operation similar to linear regression, this procedure is much easier to implement in Python when you're dealing with a high-order polynomial regression, because you don't have to build the matrix with complexity. Building this matrix is really easy in Python. NumPy.1s, now xi times NumPy.1s, xi squared times NumPy.1s, and so on. Okay? That's how we will do it. Anyway, similarly, for the right-hand side, you multiply the transpose of A with B, and you get a vector, a row vector with two rows. Okay? A column vector with 2 rows. Right. So now when you compare this to the system that we obtained previously, again, n was 3 in our example. This was the system we obtained when we did the straight line regression. Some xi is x1 plus x2 plus x3, some xi and some xi squared, a0 times a1, and then some yi and some xi yi. Okay? It's a sleight of hand, just to simplify things. There's nothing too deep about this. Okay? It's just another way of implementing regression in your Python code, but it's much easier. This is much easier. For a first order regression, or even second order, you can build the matrix manually yourself, but for anything beyond that, this is much easier. Okay? This procedure is much easier. So now in general, now we're going to throw in a bunch of numbers, m and n and m, and even I get confused by those, so let's try to keep up with this together. So given n observations, we want to fit a polynomial of order m such that the number of data points n is greater than the polynomial order m. pardon me, if it were equal or like similar to it, like n minus 1 order, then we get an interpolation. We want to make sure we're not getting an interpolation, okay? So more observations than degree of polynomial. So for example, m could be 3, and you can have 1,000 data points, okay? Y model is given for a general polynomial. This is the model for the general polynomial. And then we do the same thing. We apply the model to each and every observation. We apply it to x1, we apply it to x2, and we apply it to xn. Now remember, we have m plus 1 coefficients over here, and we have n observations, okay? Keep that in mind. So now all of these are going to result in a matrix, in a system of equations that is overdetermined. Think of the example where we had only 3 points. We had a matrix that had 3 rows and 2 columns, okay? More equations than unknowns. Same thing here, but this is for an mth order polynomial. So when you convert this into matrix form, okay, I know you think this is going to be annoying, but it's much easier to implement in Python. It's really, each column is 1 line of code. What you get is 1s on the first column, xi on the second column, xi squared on the third column, and so on all the way to xi to the power m. Okay? So that would be our matrix. Now this matrix is non-invertible because it's not symmetric. It's got n observations, so it has n rows, but m plus 1 columns, because you have m plus 1 coefficients. Okay? Each row is the model evaluated at the ith observation. So first row, model evaluated at observation 1, observation 2, and all the way to observation n. Okay? So when we put this together, we get a non-invertible system. A phi equal b. And the size is n by m plus 1, and this is m plus 1, and this is n by 1. Okay, because you have n observations. So this system is messed up, we cannot solve it. But then all we have to do is write it in this form, and then do the transpose. So what I'm claiming is that this operation actually results in the regression equations that we saw before. The benefit of this is that, and we will get a chance to see this, is that implementing this equation in Python, this matrix in Python is much easier than implementing the resulting system, whatever results from here, okay? Because that one, the way you generate it, you generate essentially column vectors of 1 xi squared, and then you just put them in a matrix and you multiply it by the transpose, and there you go, okay? The two are 1, so both approaches are the same. So if you consider each of the previous approaches for a first order polynomial, given n data pairs, x1, y1, x2, y2, xn, yn, the least squares regression to a0 plus a1x results in this system. We saw this before. Okay. Now, your job is to form into groups. You got 3 minutes, and I want you to use the normal equations to show that if you apply the normal equations to n observations, you're going to get this, okay? I'm going to put the slide on the normal equations. Hold on. By hand. Do it by hand, please. Yeah, you got 3 minutes. So essentially with these guys, what you do, you apply the equation to each observation to formulate the coefficient matrix A. Okay? And then you multiply it by A transpose. Okay? But do this for n points. Over here, I did it for 3 points. Okay? I want you to do it for n points. So put dot, 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 x all the way to xn, and then do A transpose times A, and show me that you get the original system of equations. Okay? You got 3 minutes. I know it's a little bit hard because this is the first time you do it. So give it a shot, please. So remember now, in this case, you have n observations, not 3. So the way the normal equations work, you apply the model, which is a0 plus a1x, to each and every observation. Okay, and you put those in a matrix.
don't think I did correct.
Yeah, but I want you to show A and A transpose and multiply them with each other, okay? But that's the correct answer.
Is A and A transpose always going to be like a 1 by 2 or a 2 by 1?
Yeah.
Okay.
Yeah. Well, it depends on how many observations. It's going to have n observations, right? So the row, the number of rows is going to be equal to the observations, and the number of columns is going to be equal to the order of the polynomial plus 1, right?
I guess either rows or columns, one of those is always going to be equal to 2.
No.
No?
No, because if I had a third order, if I had a second order regression, we would have one more column.
Okay.
If we had the fourth order, because each column represents one of the coefficients in the model, okay?
Okay. I think I get it.
So just take the model and apply it to each and every observation, okay? And then try to form a system of equations. You guys got it? Well, only for a first order polynomial, so a straight line. Okay. That's right. Oh, but you're copying slides.
So I mean, we would take this matrix, right, and transpose it?
No. No.
Okay. So then do we take this?
No, it's not. So think about what we're doing. We're finding a different way to get to this matrix. And that method is to apply the model to each observation. That is going to result in an unsolvable system. But if you form that system and multiply it by the transpose of the coefficient matrix, that will result in a solvable system. That's it. Okay. Have you made any progress? Okay. So I'm gonna work on the answer with you. Okay. Let's take time. I know this can be a confusing concept right now, guys. Please follow with me. If you got questions, wait until I finish with the derivation, please. So I know this is a little bit, wow, what are we doing here? This is confusing with what we're doing before. Let's just simplify. You don't overcomplicate things. Let's just simplify it. What we're doing is just another way to get to the system of equations. And I'm not going to help myself by looking at the equation. So what we're looking at is another way to get to this guy. Okay? Just another way. And that procedure was take your model, apply it to each and every observation, form a system of equations. That system of equations is not solvable because we have more equations there than unknowns. Okay? By definition, that's how we set up to do it. Okay? And then form that system of equations multiplied by the transpose, and you'll get this. Let me show you. So our Y model, my handwriting has improved. So
That's really pretty.
you got A naught plus A1 x. Okay? And we have x1, y1, and x2, y2, xn, yn. A total of n observations. I want to apply this model to each and every observation, just like we did with polynomial interpolation, with interpolation. So at y1, we have a naught plus, or at x1, let's do it the other way. At x1, we have a naught plus a1 x1 equal y1. Agreed? At x2, we have a naught plus a1 x2 equal y2. At x3, we have a naught plus a1 x3, at xn, we have a naught plus a1 xn equal yn. Okay? Now this is a system of equations that's not solvable. But let's write it in matrix form. So that's going to give us 1. So if we write this way, we have a naught and a1 over here, correct? In the first equation, the coefficient of a naught is 1. So we have 1. And the coefficient of a naught is of a1 is x1. In the second equation, the coefficient of a naught is 1. And the coefficient of a1 is x2. And then 1 and x3, dot, 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 1, xn. Okay? On the right-hand side, we have y1, y2, y3, dot, 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 yn. This is unsolvable because this is n by 2. It's not a square matrix. So if this is A, and this is phi, and this is B, then we claim that A transpose times A, phi, is equal A transpose B. We claim that this guy, when we do this operation, that's going to result with our intended system of equations. So let's do it. Let's show that ATA is going to result in that system of equations. So what is A transpose? It's 1, 1, 1, dot, 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 1, and then x1, x2, x3, dot, 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 xn times this matrix, 1, 1, 1, dot, 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 1, and then x1, x2, x3, dot, 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 xn. Now, when you do the matrix vector operation over here, what are you going to get? That matrix vector operation is going to give you, so think about it, this is 2 by n, and this is n by 2. So n and n disappear, you get a 2 by 2 matrix. And then you know that this first entry is going to be this guy dotted with this guy. That's 1 times 1 plus 1 times 1 plus 1 times 1 n times. It's n. Now this entry is this row multiplied by this column. It's x1 plus x2 plus x3 to xn. So it's sum of xi. x1 plus x2 plus x3. Same thing here. For this entry, it's the second row times the first column dotted. So that's x1 plus x2 plus x3 to xn. So it's sum xi. And finally, this guy, it's the second row times the second column. x1 times x1 plus x2 times x2 plus x3 times x3 all the way to xn times xn. So that's sum xi squared. Okay? Same thing on the right-hand side. Thank you so much. Okay, these are called the normal equations. Okay? We will see you on Thursday.